Friday next, the week after next week. We got 2 weeks to work on it, including, today, the rest of today and the 2 weeks, you actually have 16 days. A little bit more than 2 weeks if you work on it during the weekend. So the first is the two problems here. Okay, this is the one we used the last semester, is the D flip-flop. If you follow the textbooks, wherever you have, the D flip-flops looks different from this one. It's not making sense, right? You learn how to make a D flip-flop, but if you are trying to use it for something, it doesn't work. have to Google it. So this is what we Googled last semester. How to find like this structure really works. It's not because of the logic. It's because it doesn't have the ones. I'm going to draw it for you. I think we did it in logic very short, briefly. So the D flip-flop, the traditional D flip-flop we have been using, which came from the JK flip-flop structure, it doesn't have a set and reset. You couldn't set and reset it. So if you have a D flip-flop, you couldn't set and reset, you just couldn't use it, because everywhere I've been using a D flip-flop in the circuit, they do require set and reset functions. So this one only has a reset, but doesn't have a set. So I'm gonna, introduce the functionality of this one first, and I will let you guys to add a set to it. It's pretty simple and straightforward. You will know how to do it, no problem on that. And the second one is a D flip-flop from the TI chip. So you can buy a D flip-flop chip from TI. Again, this is not from the textbook. The textbook doesn't have this structure. I have to Google it. So this is where I Googled it, and we found out the functioning chip, TI D flip-flop chip. And then we got into we found the data sheet of that chip and found the schematic in there. But you can see the schematic somewhere else as well. It's just not in the undergraduate level textbook. Very interesting. So this one is pretty good. Can do set and reset. It's ready to use. If you build it in LTSpice or where's that? Yeah, electric VLSI, it should work and do both. So when you are running the simulation, I'm going to ask you guys to not just test the logic, but also test the set and reset function. You know what I mean? So if you do not have a set and reset activated, it shouldn't set or reset. Just do so D comes, whatever D is, can be 0, can be 1. The clock is going to send D at the rising edge to Q. And Q naught should be the inverted version of it. And when you set or reset, you'll have to do both in order to verify the logic. The result, if you set the result, it should be what? If you set it, it should be what? If you set it, come on, if you set the circuit, it should be 1. You should get a 1 as a result. If you reset it, it's been reset to 0. So these are the two problems in homework 9 in this document, but also there's another one for 2 weeks, right? So there should be another one. And click it, you find out this is a web page I had for the semester, from last year in the spring. But I just put the link. I'm not going to make any changes to it. This shows you how to make the sequencer and code register for the start block. I'm going to introduce these two components pretty soon. So these are the D flip-flops, and we put this one into a symbol. So whatever here, this is a TI D flip-flop, has a set and reset, it's ready to use, right? Like I just said. And this is that TI D flip-flop. It's one D flip-flop, okay, with a set and reset. So you just draw this one in LTSpice, make a symbol, and reuse it in the upper level structure or circuit. Okay, so this is a 4-bit. This is a 4-bit star ADC. We need 5 bits because when we are running that star algorithm, we need 5 states. Remember, so if it's a 4-bit, we need 5 circles, 5 states. If it's 8-bit star ADC, we need 9. So we need 5 flip-flops, 1, 2, 3, 4, 5, to hold these 5 states. Okay, I'm gonna let you know how this works pretty soon. On the top is a sequencer, and the bottom is a code register. And here's a simulation. So I'm going to expect the same result. If it's functioning, if your SAR block is functioning, you should see the same thing here. So instead of just drawing the circles and doing whatever on the paper from anywhere from the theory, right? I prefer hands-on. If you learn it, you have to implement it. So this is where you implement it. You run the simulation, and you see all these A's, right? Until you get the correct result. So which means the SAR block works. Okay, so you'll know how to build it. This is reviewing the SAR algorithm. And I made everything here into one symbol, the SAR block. And then I simulate it. Okay. It's not wasting your time because first you can learn a lot from this, and also it's not a large circuit, but for a relatively larger than the previous ones, how do you simulate it? Think about find a strategy to simulate so many ports and make it very clear to the audience as a result to present it, right? Eventually, you have a symbol like this, and it's gonna sit in your library on your computer. Make sure you have a back it up, okay? Have backups. It's a lot of circuit because you are going to reuse it later. So the overall project for this class is going to be a SAR ADC. Okay, so we are building an ADC here, but probably not layout. This will be one of the very important part of the ADC. If you have this one already sit in the library, whenever we are moving forward with the other parts components of the ADC, you can directly grab it and put it in there for the simulation. It's not wasting your time. It's part of the project. We just start doing this earlier, just taking baby steps. If I directly assign you a course project, like just make a SAR ADC, you don't even know where to start with, right? So let's just take all the baby steps. If you finish this SAR block within 2 weeks, and I think we still have time to make a sum and hold, we make a comparator, and then eventually the dual registers, and then eventually find out you have everything for the SAR ADC. So eventually just put everything together and make a schematic, it works. It could be good evaluation to the teaching evaluation results. Great. One quick example, let's review the SAR algorithm. Okay. So B in is, for example, is 4.5 volts. And I guess VREF is 10 volts again. I believe so. Start with, okay, so 4-bit ADCs, 4-bit SAR ADC. Start with 1000, which is 5 volts, right? Yeah, 4-bit. .5 volts. What's next? Wait, 0 or 1? 0. No, 4.5 is the input, right? 5, yes, 0, yeah. What is this one? 2.5? Wait. It is 2.5. So 2.5. 2.5 is the results being fed back to the inverting or non-inverting of the of the comparator, remember? Inverting, right? Because here's 4.5. Yeah, and here's is keep changing, right? So 2.5 versus 4.5 is going to give you 1. 0, 1, 1, 0. And this one becomes 3.75 volts. 0.75 volts here compared to 4.5 is still smaller. So you're expecting a 1 again, right? So it becomes 0, 1, 1, 1, right? And this is 4.375 volts.
It's the same state there.
Yeah. That's pretty close to 4.5, right? As a 4-bit ADC. So we got a result. So you can see that this 1 here at the very beginning is being shifted to the right. So I have to design a circuit to shift it. Okay. So let's assume we have that kind of circuit shifting that one on the top. So we have another one at the bottom. It's called a code register. Let's do that first. So we have 4 bits. We need 5 D flip-flops. Okay. Here's a set on the top. So when you give a 1 to it, it sets Q. Q is a result for the D flip-flop, or the output of the D flip-flop, Q. Right? It's being triggered. It's a rising edge flip-flop because I didn't draw a bubble here. If I draw a little bubble here, it's a falling edge triggered. So that's a set pin of the D flip-flop. And I got a pin for the input as a D, data, right? D. And the circuit is being shorted like this. So the Q is being used as a clock for the previous D flip-flop. I'll explain why that. And the comparator's output. Comparator is being shorted to D. Oh. And why this works? Think about it. So for example, I have something else on the top, okay, which is able to shift that 1 to the right. So at the very beginning, I'm going to assign 1, 0, 0, 0, 0 to the circuit, to the set pins. Yeah, 1 assigned to here. If I have a circuit, it's able to connect to the set pin and assign these values to at the very beginning. Just assign these values from the top.
Extra bit.
Where's the extra bit? Oh, the 5th one? Yeah. I'm going to show you why we need it, because we need this one as a clock for this one.
So you just automatically throw 0?
Oh, no, you don't have anything for now. It's like this, perform like the same as this one. It doesn't have, but it doesn't have because eventually you have 1 bit, you need to shift it out. So when you shift out the last one, there should be something to hold it. That's one part. Another part is this one is providing a clock. You need the one extra one to provide a clock for this one to register it. So the data, when data is here, you need a rising edge to store it from here to here. So it's going to be latched to this point. Let me draw the outputs. So this is B3. It's B3, and this is B2. B1. B0. That's all the output. This one is not providing an output. It's just being used as a clock. Because the last bit was shifted out, and we are not using that anymore, which actually is the very beginning, the one here. It's out. We don't use it. Eventually, you think about all the shifting here, right? So this one was moved to here, right? So this one becomes here, and then here, and then here. What about the last one, last state? You don't have it anymore. It's out. So we don't need it. So there's no output pin for this queue. It's out. It's just over there. We just don't use that pin. It's just a clock. I'm going to show you why we need a clock. So this one, it doesn't need a clock, yes. Because we are not using this one as a clock. Whenever we set it, right, when the one is over here, it's set. So you got a one here, and this one is used as a clock for the previous one. But we don't need a clock for this one. Why? Because we don't need anything to be transferred from here to here. It's just the one here is being shifted to the right. Let's go through all the steps here first. So you'll find out. It's not that difficult. All right. So whenever, for example, there's some kind of magical circuit, some magical circuit on the top, kind of shift that one to the right. Just making one here and one here. So whenever one is being shifted to here, this one becomes 0 automatically. A circuit can do it. Okay, don't ask me why. Don't show that kind of face. Okay, it's doing it. All right, it's doing it. Let's simplify the process. If you ask question why, then it's going to be another 15 minutes to explain why. So let's just assume there's something. I'm going to show that circuit next. Okay, let's don't put everything together. I want to make sure everyone understands it. We haven't done too much here. You are late, but it's fine. Okay, because you know this, right? Yeah. So then I just started drawing this schematic, and these are D flip-flops. So D flip-flop at the rising edge, when the rising edge comes, it's going to send D to Q. That's it. That's how D flip-flop works. Okay. And whenever it's high, it's going to hold the value at Q and waiting for the next rising edge to change it, to update it. Otherwise, it's holding the previous state. It's not changing it. It's called the rising edge triggered D flip-flop. Okay, and the two structures I just showed you, I recorded. So you look at these two structures. So these two structures of the D flip-flops, these are both edge trigger D flip-flops, and you want to know that the edge trigger D flip-flops are very important. They are the actual D flip-flop being used in your CPU. So the CPUs are just billions of D flip-flops in there, I guess. It's just D flip-flops, or lookup tables or other decoders or logic circuits, but most of them are just D flip-flops. And then, okay, comparator's output. So what is a comparator's output? Remember, you compare it, but it happened in your mind. We don't have a circuit here for the comparator, but it happened in your mind. You are comparing which one is bigger, right? If this one is bigger, the output's of 0. If this one is bigger, it outputs a 1. So there's a comparator output will give you 1 or 0s, which are the numbers you plug into the sequence here. Remember, that's what you plug in actually as a comparator's output. So this is a comparator's output, or the new numbers you plug into the result. Okay. At the very beginning, a magical circuit on the top. Assign 1 and all zeros to all of the circuits. So 0 is won't do anything. So 0 to the set pin here we'll just set it into the D flip-flop mode. It's going to perform like a D flip-flop. Rising edge comes, send D to Q. When set is 0, which means you didn't turn on set. You give a 0 to set or turn it off. So it's not setting the Q. So setting means you're setting Q to 1. Resetting means you're resetting Q to 0. Make sense? Make sense or not? No, probably. So set, keep in mind, in digital circuits, set is set it to 1. Reset is reset to 0. Okay. All right. So this is a set pin. Okay. If I turn it on, it's going to set which to 1. Q to 1. If I put a 0 to here, what is this one doing? Wait, no, set. I don't have a reset pin. I can design a reset pin, but I don't have it now. I'm not using it. It's not doing anything. So if you have a set pin here, I need a 1 to set reset pin to reset it. Make sense? It's just like a switch. You turn it on or off. So this switch is setting Q. This switch is resetting Q, right? But I do need a 1 to turn it on to activate it, to set or reset. Okay, so this is a set pin. I need a 1 to set Q to 1. If I put a 0 here, Q is not doing anything. It's just following the D flip-flops mode. Whenever rising edge triggers it, sends D or the data to Q as a D flip-flop mode. But when you have a 1 here to set it, no matter what D is, and no matter it's rising edge, falling edge, it's not going to change the result. It's going to be 1 forever. You're setting it forever. Okay, so now you know how to use it. It's just like a chip. And what I just said to you guys is how to use it, like user manual or something, right?
So for our first stage, right?
Yeah.
It gets set.
Yeah.
So it's a 1.
Yeah, so 1. 1 is going to be here, right?
Yeah.
Okay. So 1, 0, 0, 1, 0, zeros. You are thinking, why these are zeros, right? Because at our beginning, you didn't do anything. These are just nothing. You are not expecting a chip. You just grab from the drawer. There will be some charges accumulated at the pin. It's just nothing. Right? This don't even have a clock. These are zeros, right? So zeros, zeros, zeros. It's not even the rising edge. Nothing is going to be pumped from D to Q. Nothing. It's not exactly zeros, but they are very low voltages. Nothing, just nothing. 0.1, 0.2 volts, probably. So at the very beginning, you got 1 zeros, right? No problem on that. So 1 zeros. Okay. Next. Okay. I'm gonna some magical circle on the top is gonna move this one to the right. Okay. This one becomes here, and this one becomes 0. Okay. So for all these set pins, only this one is 0. Oh, it's 1, but all the other ones are 0. What's gonna happen? We got a 1 here. What's gonna happen? Yeah. Okay, so yeah, so this becomes 1, right? Which you expect because you are moving that one to the right. And this one, because it used to be 0 and now I got a 1 as the rising edge. And the rising edge is performed like a clock. It's going to trigger that D flip-flop and send this one to here. So whatever the comparator has, that will be, which is a comparator result here, will be plugged into here. So there's 0, 1, 0, 0. Got it? They shift that one to here, and now this is the only one has a set, but all the other ones are zeros. And this one's gonna set this guy, okay? And this one has been updated already because you are right here in this state. This one has been updated. So this one becomes 1 here, right? Makes sense. And this one is gonna trigger, is like a rising edge, so trigger this D flip-flop and moving whatever the comparator has to the second digit. It's a rising edge. And D will be sent to Q, which becomes B2. Make sense? Okay, and then just keep moving so you can plug in all the numbers. No, because this one, oh, you mean after this one becomes 1? Let's see. You got a 1 here. Oh, you got a 1 here to update this one. You know what I mean? This one that never got changed. So this one got a clock and update this guy, and then you got this one update this guy, but this one will never be changed. And this one is the one to be changed, which is okay. That's what you are doing. This one will be set and then trigger it and then send it here. And then it will never be changed anymore. Right? If you move to next, it's going to change to this one, but not this one. Right? But this one was 0, right? If this one is 1 becomes input for this set, and it's going to give a rising edge here, and it's going to send the data here. If this one is 1, to be changed from 0 to 1. Oh, it was 1. It was 1. Yeah. Yep. It was 1 here, right? Yeah. Really get down to the very bottom level of the logic. So how do we make so this is called a code register. It's the name of the circuit. It's registering all the code here. Code register. And on the top it's called a sequencer. We need to design a sequencer now. Also D flip-flops, sequencer. How do we make a sequencer out of it? Also five D flip-flops on the top.
So is it always just your number of bits plus 1? For sorry.
Yes, yeah, for this one, yes. And I think the sequencer we have to give a reset as well. Let's see if that's true. Reset. Okay, set on the top, reset at the bottom. Set, reset. DQ. Okay. So these Qs are being used as the bits connected to the set pins here at the top. These ones. This is we have 5 at the bottom, so we need a 5. And then these are also being fed into the D for the next stage. And reset. This is the name of the pin, okay, name of the signal. So the reset signal is being shorted to the set for the first one. It's very confusing, being sent to the set of the first one. And then connect to the reset of all the following ones. Here.
The reset for the first one is connected to this.
Yes, that's just the name of the signal. Okay, it's just called the reset of the whole circuit. It's just a name.
They're all short together.
It's just a signal. But you short the set of the first one to the reset of all the following ones. Okay, and then you feed a signal to it, and the name of the signal is called reset. Anyway.
If you reset the circuit,
Say it again?
it makes sense if you reset the whole circuit, you want it to be 1, 0, 0, 0.
Yeah. You want the first one to be set, right? Yeah. You want the first one to be different.
It's special. But when you just call it set, because you're resetting the whole circuit.
Yeah. That's right.
Or are you setting the whole circuit?
I see. Okay. Clock.
You're resetting.
Clock. Okay. So clock is just a clock from the whole system. And now let's take a look at it. I'm going to give you a question. Ask you a question later after I explain this, right? The first time, if you give a 1 here, what's going to happen?
Give a 1 to the clock, 1 to the reset. It will set Q to 1.
Yeah.
Call V1 depending on the clock.
Right? Yep. Okay. And then these will be sent to the code register. Yep. Here, right? This is what we expect. We actually need that 1 0 zeros, right? But now let's shift it. How do we shift it? If you keep a rising edge, right? Rising edge, what's going to happen? The rising edge is going to send that 1 to here, right? And shift all the zeros to the right. So this 1 will be shifted 1 by 1, but however, what's going to be, how to do it? So after you do this, right? So wait, I'm just asking where this one should be shorted. Yeah. So you just need a 1 0 for the whole thing, right? That one, no, just 1 1 for the whole thing, and you are shifting that single 1 to the right. So after you shift this out, you need everything else to be zeros. So don't connect this one to anywhere else, just 0, right? So after this one is being shifted to here, you need this one to be replaced by a 0. So if you put a 0 here, then you keep getting 0 in the front. But this 1 will be shifted to the right. That's how we make it happen. Make sense? Okay. That's the core of the star ADC. But there are so many other things that are important as well. Okay. Now let's look into different flip-flops because we have to build different flip-flops to make it happen, right? Different flip-flops. So if we talk about different flip-flops, we have to start with latch first. SR latch. Do you still remember that? No. Okay, Q and Q naught for the output of the SR latch. You probably will see OR gates, NOR gates for the SR latch, which is fine, but I just use all the NAND gates. It's going to do the same job, but just swapping the I's and R's. So SR latch is set reset latch. It's setting and resetting Q. Right? Whenever we are talking about setting and resetting, it's usually always Q. Q naught is just the inverse of Q. So you are setting and resetting Q. Keep in mind. So let me know which one's S, which one's R for the inputs. Where did I ask you? Logic. Yeah. Which is S, which is R? Okay, let's see. Okay, if we turn on S, give a 1 to it. This one must be 0, right? So keep in mind, we never use 1 1. We never use 1 1, do we? No, we never use 0 0 for the NAND gate SR latch. Pay attention.
Okay. I mean, you have a 50-50.
Yeah.
Here, you guess S on top, R on bottom. Yes, R on top, S on bottom. Where
you want to start with? Let me know. Okay, very simple question. For this case, I assume this is S is R, right? If it's not working, then we just. Okay, so now where do we want to start with, and why? No. You don't know because it's a NAND gate. 1 is not going to determine the result. Yeah, you want to start from here because 0 is going to kill this NAND gate and give you 1 here, right? Because 0 and everything will be 1 and not will be No, 0 and anything will be 0, and inverted will be 1. So this is definitely 1. And 1 will be fed back to here, so we got 1, 1, got a 0, right? You want to reset it, but you want to set it, but you are resetting it. So it's not right. Okay. And the next one is SR flip-flop. So this is clock. Q naught, which is S, which is R. Why is it called flip-flop? Because it's being clocked. So latch is just a latch, just store it. One more question. It can be in the interview. Okay, so for this SR latch, when you operate it, you only have 1001s. Keep in mind, since you are using this to set or reset, it's not making sense to use 1100, but it happens sometimes. So let me ask, if you have RS to be 00s, what's going to happen for Q? 00 for this NAND based SR latch. If you have 00 for both, then what's going to happen? So when I was in college, I reading the textbook. It's saying, hey, for this SR latch, 00 is abandoned, or it's not allowed to be used. You shouldn't use it like that. But what does that mean? It's going to build a fire in there, or it's going to fry it? What's happening? They never explained to us. What's going to happen? It's just like 1-1 for Q and Q naught. And then what's going to happen? So this will be the voltage being held by Q and Q naught. This is 2 pins, even though I name it as Q and Q naught, but they won't be fried, right? It's fine. It's still going to happen, but we just don't use it. But you shouldn't say like it's not allowed. Like you feel like it's very dangerous to something. Or on the other type, yeah, it's not allowed. You shouldn't use it. But if it happens, it happens. Make sense? Okay. So what about 1-1? You couldn't tell. Yeah. So it's called memory. That's why it's called a latch. It's storing the value there. It's not changing it. It's feeding back and make it really stable. Very stable. So it's a memory. It's a latch. It's not doing anything. But when you have 1001s, it's setting and resetting queues. Got it? That's how you should explain SR latch to whoever interview you, right? So for SR flip-flop. Which is S, which is R. Where are the inputs? Right? Which is S, which is R. It's pretty obvious because whenever the clock is 1, this will be enabled. If it's 0, it's not enabled even. If it's 0, it's always 1. It's not doing anything. Okay. Again, 1-1. When the clock is 0, you're getting 1-1, right? Okay. No matter what the 2 inputs are, you're getting 1-1s. So 1-1 is what? Should do it faster. Yeah, it's latch is memory. Okay. It's not changing anything. Okay. So whenever clock is 1, it works. Okay, it works. Okay. So whenever clock is 1, it's not affecting anything. So whatever here works. Which is R, which is S. Flip them together. Why? Because it's an inverter, right? It's not an inverter. It's a NAND gate, but it's an inverter because this is 1. Whenever we got a 1 for one of the inputs of the NAND gate, it's an inverter. Since you hook this to VDD, this becomes an inverter. No difference. right? Okay, so whenever this one becomes 1, it starts working, and then this works. Okay, so you want to determine which is S, which is R, because these are inverted. That's why RS here, SR here. Okay. One quick question here. So is this edge triggered or level triggered? So whenever you have a clock equals 1, if data changes here, is that going to affect Q? Yes. So it's bad. It's bad. When clock is on, yeah, when clock is on, you have to make your clock super fast, way faster than your data change, right? So and then you are still taking chances to not getting any errors. So it's bad. You have a pretty wide on time compared to the edge. Just sample it. So the level trigger is bad. So now let's look at the D flip-flop. Very simple version of the D flip-flop. It's very similar to the SR flip-flop, which is short, 2 lines. Just short the 2 pins with a, it used to be S and R, but now if I short it with an invert, not short actually, if I invert it, so this pin is going to be called as D, right? This becomes D instead of something else. I'm not using this pin anymore, so I just call it as D. Why it makes sense? Why is it D? Why is it data? Because data, so D flip-flop is just being sent to Q, right? Whatever D is, you're expecting at Q whenever a clock arrives. That's a D flip-flop. Transferring the data, you're clocking something, right, to send the data from here to here. Why? Why D should be here, not here? No. Why D? Because I have 2 pins, 2 inputs for the SR flip-flop, right? But if I connect these 2 pins with the inverter, and now I just have 1 pin instead of 2, because I just use one of them. But why I should define this one as a D, but now this one is a D? Yeah, true. Why? Because when S is 1, you are setting Q becomes a 1. So because digital data is digital data, is 1 is 1, right? Seems to everyone is like 1 is being sent to Q. Because when you set it, you put a 1 here. And this one is being set, you got a 1 here as well. So whenever you turn on S, you give a 1, and you got a 1 here. So it's a 1 and 1. Okay, it's the data being sent to here. 1 will be sent to here. And if you're 0, because this is being inverted, so this one is 1, you turn on the reset. Okay, so if you have a 0 here, you got a 0 here. Make sense? It's level trigger. Why? Because when clock is 1, it's always happening. It's not a edge triggered. Okay, we'll talk. No. So moving to edge triggered, the textbook version and the simplified version, and also the ADC version next Monday.
Who's the exam?